Jai Hind students, in the last lecture of this satellite communication, we discuss about various orbital elements that are eccentricity, semi-major axis, right ascension to the descending node, then inclination, argument of perigee, time of perigee, and these are the all points which are required to locate the satellite in the orbit with respect to the earth. So now we are going towards the satellite link design. Actually, from starting I am telling you one point that whenever we want to locate a satellite, our first requirement is to locate that satellite into the space in the orbit. That we will done already. But the main function of a satellite is to maintain the communication between the earth and the satellite. Means there is a direct connection between the earth station and the satellite which is located in the orbit. It means there is a link between the earth station and the satellite, and that link is defined as the satellite link, and now we are discussing the design of that satellite link. So a satellite link is defined as the earth station satellite earth station connection. The earth station is basically the satellite segment which is located on the earth, and the frequency on which, or the link on which, the satellite is contacting, earth station is contacting to the satellite in upward direction, that is called uplink, and when the same satellite is connecting with the earth station, that is called downlink. So basically when we want to describe this satellite link design, actually we have to also design the earth station design. So when we want to design that earth station, that designing consists basically 2 points. First one is the transmission link design or the link budget, and second one is the transmission system design. So these both are related to the earth station design, or for the satellite link we are actually talking about the uplink and the downlink. So this link budget established, that link budget is related to the earth station. That link budget established the resource needed for a given service to achieve the performance objective. Means when you are want to design a satellite system complete for a specific task, such as for navigation or something else, you have to find out the resources needed as per the service which we want to use for a specific objective. So that is the about link budget. Now for the satellite link design, the 4 factors are related to the satellite system design, that are weight of the satellite, choice of the frequency band, atmospheric propagation effects, and multiple access techniques. Other than that, 2 things are also that major frequency band for uplink and downlink. Actually we are having single convergent transponder, means 6 GHz uplink with 4 GHz downlink frequency. Double convergent transponders means 14 GHz uplink and 11 GHz downlink. 30 to 20 GHz advanced transponder that are using 30 GHz uplink, where the downlink is 20 GHz. That uplink frequency in the satellite design, satellite communication case, uplink frequency is always greater than the downlink because of the path losses and the power requirement factors that I already discussed in the previous one. Now at geostationary orbit, this is already satellite using both 6/4 or 14/11 GHz for every 2 degree minimum space to avoid interference from uplink earth station. So these are the main factors that are used for the satellite link design. Now how it is going to describe? You can see here, this is a maritime navigation system in which you can see that this is the gateway earth station which is located on the earth, and this is the satellite which is placed in the orbit. This is a maritime satellite, and that maritime satellite is connected with this earth station, gateway earth station, with the Ku band uplink and downlink, and they are using the L band uplink and downlink for these aircrafts locating the various ships in the ocean. So this is about the maritime satellite. This is a just example of a satellite link. Means now you are going to design the same system. Means if your objective is to create a maritime navigation system, then first of all you need a maritime geostationary satellite or something else. That satellite is using Ku band to connect with the earth station. You are also going to design the earth station with respect to that. Similarly, you are using L band for uplink and downlink. So these all are the examples. Now satellite link design steps. So when we are talking about satellite link design steps, actually satellite link design actually have two concepts. The both concepts are related. In first one we are talking about the only theory or the concept or the phenomena, but in the second one we are going to derive the equation or the satellite link equation. That satellite link equation will be derived in the next lecture. Today we are talking about the concept and the phenomena. So for the satellite link design, the RF carrier in any microwave communication link begin at the transmitting electronics and propagate from the transmitting antenna through the medium of free space and absorptive atmosphere to the receiving antenna, where it is recovered by the receiving electronics. Means here you are using radio frequency carrier for microwave communication link, which is beginning from the transmitting antenna and at the receiving antenna, also considering the free space and absorptive observation or atmospheric conditions. Now the carrier is modulated by a baseband signal so that the transfer information for the particular application. Also the first step in the designing procedure or designing the microwave link, because all are in the gigahertz range and gigahertz range is representing microwave link, that microwave link is to identify the overall requirement and the critical component that determine performance. So for this purpose we use basic arrangement for the link shown in this figure. So this is the diagram. Here you can see that this is the earth station part, this is the satellite part. In the satellite we have a repeater circuit with a receiving and a transmitting antenna. Receiving antenna is connected to the earth station with uplink frequency, whether the transmitting antenna of satellite connected with the receiving feed of the earth station with downlink frequency. So at the receiver or transmitting side, you have getting the information from input, you are performing the encoding. After that modulation will be performed, then up conversion of the signal and high power amplifier to apply that signal with the high input impedance, high output impedance, and you are sending that data towards the satellite. Similarly, from reception you are taking a signal and using a low noise block converter so that noise can be minimized, then receiver and demodulator, and then decoding, and you are getting the information at the output. So this is the basic structure of a satellite link design. Now the basic consideration for satellite link design, here you can see that for free space attenuation is determined by the inverse square law, which states that the power received is inversely proportional to the square of the distance. Means when we are designing this satellite link, actually we have to consider various things. The main thing is related to the attenuation. Attenuation is basically the degradation in signal due to the atmospheric conditions. So this free space attenuation is present here, and actually that free space attenuation is calculated or determined by this inverse square law, that shows that if your received power is PR and the distance is R, means that PR is inversely proportional to the distance R. That is the consideration for the free space attenuation. That is very much required for this satellite link design. Similarly, there are a number of additional effects that produce a significant amount of degradation and variation, because other than this free space attenuation, other atmospheric conditions are also there. That atmospheric conditions are rain, terrain effects such as absorption by trees, walls, some less obvious impairment produced by the unstable condition of the air and ionosphere. Because you know that due to the atmospheric changes or weather changes, that condition of air and the condition or density of the ions in the ionosphere, outer layer of the atmosphere, is always going to change. That is also creating some kind of attenuation. Also, the required factor include the performance of this satellite itself. Also, the other consideration are the configuration and the performance of the uplink and the downlink earth station, that is related to the earth station design. Also, the impact of the propagation medium in the frequency band of the interest. Means for the system which you are designing a specific frequency band, what is the impact of propagation medium. So these are the consideration. Other than that, bidirectional communication means both direction communication, satellite to earth station and earth station to satellite, occurs with a separate transmission from each earth station. Similarly, due to the analog nature of the radio frequency link, each element contribute a gain or loss of the link, may add noise or interference as well because of the individual system. Because if you are using an amplifier, it means that amplifier is also contributing in the form of a gain or loss of the link. This result in overall performance is presented in term of the ratio of the carrier power to noise or information quality, means C to N. Means you are going to design all overall performance result in this C by N ratio, that is carrier power to noise ratio. Means any uncertainty can be covered by providing an appropriate amount of the link margin which is over and above the C by N needed to deal with the propagation effect and non-linearity in the earth station and satellite repeaters. So these are the basic consideration. So when you are going to get that equation, that is the further process, but you have to identify or remember all that point by this diagram. Here you can see that actually this complete is about the service quality, and service quality is related to the bit error rate which is coming from the C by N ratio. That C by N ratio is coming by the various parameters, and actually that's in C by N calculation, uplink EIRP, isotropic radiated power, input radiated power, then uplink pattern advantage, transponder gain step, downlink pattern advantage and receiving antenna gain. These are going to add on in this carrier to noise power. But free space losses, waveguide losses, atmospheric losses, rain attenuation, tracking errors, that are going to minus the carrier to noise power. Similarly, E by S intermodulation, uplink thermal noise, downlink thermal noise, transponder intermodulation, co-channel, that are coming on the satellite side. So these are also going to play an important role in the C by N calculation. So now satellite link design. Actually till now we are talking about the satellite link design, means we are going to design the uplink and downlink links. But now we are talking about the calculation part. So satellite link budget is a set of calculation giving the feasibility and performance summary of a particular communication link from the transmitter to the receiver end. Actually, this link budget determine antenna size to deploy, power requirements, link availability, bit error rate and overall consumer satisfaction with the satellite service. These all points are related to this satellite link design. So link budget is a tabular method for evaluating the power received and the noise ratio in the radio link. This is the complete about satellite link budget. Now the link budget must be calculated for an individual transponder, means if you are using KU band transponder, K band transponder, C band transponder, means for each and individual transponder you have to design, you have to calculate the link budget, and that must be recalculated for each of the individual link also with respect to the earth station. And C by N ratio calculation is simplified by use of this link budget, means that C by N ratio also playing an important role in this satellite link budget analysis. So evaluation of the received power and the noise power in radio link is also there. So the link budget must be calculated for individual transformer for each link, where a bent pipe transformer is used with the uplink and downlink. C by N ratio must be combined to give the overall C by N ratio. So this is the now satellite link design methodology. As I told you in the previous one that for designing a complete satellite communication system, you have various requirement. Means you have to establish a earth station, then you have to locate a satellite in the orbit, then you have to mark specific orbital element where the satellite is going to be placed, then the link between the connection between the satellite and the earth station, then you have to analyze the budget related to this link design, means how you are going to make a earth station at the earth segment. So these all are point of the satellite link design. So now I am summarizing all these steps which we discussed earlier in step by step in these slides now. So the design methodology for a one-way satellite communication link can be summarized into the following step. The return link follow the same procedure, means you have two links, uplink as well as downlink. Here we are giving about only one link summary. Similarly, we can design the return link summary. Then the step first is frequency band determination. That shows which band you are going to use, means you are going to design for Ku band, you are going to design for C band, means for each band you have to determine first which frequency band. Then the satellite communication parameter determination, make informed guesses for unknown values, means now satellite communication means you are going to define the satellite parameters where the satellite is going to be placed. So the related parameters. Now earth station parameter determination, both uplink and downlink. Then establish uplink budget and a transponder noise power budget to find C by N in the transponder. Now you have to identify the transponder, means on the satellite which kind of transponder or which band transponder you are going to use. For that you have to establish the uplink budget. Similarly, determine transponder output power from its gain or output back off. Then in the next step, you are establishing a downlink power and noise budget for the receiving earth station. Means first of all, what you are doing, you are finding for which band, means Ku band. Then you are doing the satellite communication parameter, means where this is the earth, this is the orbit, where you are going to locate the satellite. Then you have to find out the parameters, means this is the uplink parameters, this is the downlink parameter. You have to calculate C by N ratio, means here you can see that you are doing it all for the uplink, whether you are doing it for the downlink. Now same as uplink, you are going to calculate C by N down and C by N for a station at the outermost contour of the satellite footprint. Satellite footprints mean where the satellite is moving in the orbit towards the complete structure of the orbit. So that's why you have to find out the farthest distance, outermost contour, so that you can calculate the C by N ratio for all of that. Now after calculating all these points, you have to calculate signal to noise ratio or bit error rate in the baseband channel. Then determine the link margin. After that, you have to do a comparatively analysis of the result via a specification required, because due to this comparatively analysis, you will get your specification. Now tweak system parameter to obtain acceptable C by N SNR bit error rate values, because for a specific satellite communication system, bit error rate, SNR ratio, C by N all has to be specified. And when you want to specify them, then for a given comparative analysis, you get some specific data or specific output. Now you interchange the data, means change the frequencies, change the location, change the parameter. That is the tweaking. So by tweaking this, we are getting various range of C by N, SNR and bit error rate, and out of that ranges, which is the acceptable for our system, we are going to take. Then the next is propagation condition determination. after taking out all these conditions, you have to find out which kind of propagation condition have to be faced by the signals to propagate from earth to the satellite. Then uplink and downlink availability estimation, when the basically uplink and downlink are not available for the communication. Then redesigning system by changing some of the parameter if link margin are inadequate. Similarly, are gotten parameter reasonable? Is design financially feasible? That is the most important part, because cost is always matters. If these parameters are not reasonable, it means you have to redesign this. Means if yes means for the all parameters are reasonable and design financially feasible, then it is a yes on both count of the step, then the satellite link design is successful, completed. But if it is not, then counts is in step 12 and start from the 1, because all satellite link design procedure is just stopped here. So this is all basically about the satellite link design theory. In the next lecture, we are going to derive the equation of the link, so satellite link equation, and other G by T ratio and the system noise temperature calculation also. Till then, thank you.